Hello, once again. Welcome, SS1, to a fresh topic on the functioning ecosystem still, called energy transformation in nature. So far, we've been looking at functioning ecosystem, and we looked at food web, food chain, ecological pyramids. So now I'll be talking about energy transformation in nature, still under functioning ecosystem. So you're welcome. Let's go on. What do we mean by energy transformation? That just has to do with energy changes, changing energy from one form to another. Now, these energy transformation can occur in nature, and living things such as plants and animals are the media of this exchange. So the transformation of energy in an ecosystem begin first with the input of energy from the sun. The solar energy from the sun is very important because that is the ultimate source of energy from whence all other transformation can take place. Energy from the sun is captured by the process of photosynthesis. It is only green plants via their chloroplasts that have the ability to capture solar energy. And they can then be able to convert this solar energy to chemical energy in the form of food produced by these primary producers or green plants. Carbon dioxide is combined with hydrogen derived from the splitting of water molecules to produce carbohydrates. So this is just photosynthesis. And then energy is stored in the high energy bonds of adenosine triphosphate or ATP. Adenosine triphosphate is the full meaning of ATP, and that is the energy currency of the cell. That is the form in which the chemical energy produced by green plants is conserved. It will be very important to look into the laws of thermodynamics when we're talking about energy transformation in nature. Take note, we said that energy transformation is all about energy changes. Transformation there means change. So energy changes. It means to convert or change energy from one form to another. And in energy transformation in nature, we are looking at conversion of energy from the solar energy to chemical energy. And these will be carried out by green plants. That's when nature comes in. So green plants will be the instruments, okay, that can convert these solar energy to chemical energy. And then it can then be passed along the food chain via the consumers. Let's look at the first law of thermodynamics. It will be very important you know what it states. The first law of thermodynamics states that energy can neither be created nor destroyed, but can be changed from one form to another. So the first law of thermodynamics states that energy can neither be created nor destroyed, but it can be changed from one form to another. This is also applicable in physics for the science students. And then the second law of thermodynamics states that during this conversion of energy from one form to another, some part of this energy will be lost to the surroundings as heat. So, the second law of thermodynamics states that during this conversion or transformation of energy from one form to another, some part will be lost to the surroundings in the form of heat energy. So the second law of thermodynamics is telling us that heat energy will be released during the conversion of energy from one form to another. However, the first law states that it is possible that energy can be changed from one form to another, but energy can not be created, energy cannot be destroyed. It is only possible, according to the first law, that energy can be changed from one form into another form. But even in this process of changing energy from one form to another, no new energy will be created and no energy will be lost. That means energy cannot be created, energy cannot be destroyed, but energy can only be changed from one form to another. That is the first law of thermodynamics. Now, it is possible that energy can be lost as heat energy. Remember, the first law states that energy cannot be created, energy cannot be destroyed. But the second law is saying that, however, during this conversion, some part of energy can be lost as heat energy. In other words, during this conversion, heat energy can be generated. And that is where we talk about energy loss in the ecosystem. Energy can be lost in the form of heat energy during conversions in the ecosystem. I hope that is clear. Let's take a look at ways in which energy can be lost in the ecosystem. Now, take note that we said that the media of this transformation of energy in nature will be living things. Plants and animals are the media of energy conversion in nature. Let's take a look at plants being a medium of energy loss in the ecosystem. Now, when the sun's energy reaches the earth, about 20% is reflected back by the vegetation into the atmosphere. Some 39% is used in evaporating water from leaves by transpiration. 40% warms up the soil, air, and plants, and then only 1% will be left to be used by green plants for photosynthesis. Now, when the sun's ray in the form of ultraviolet light rays falls on green plants, falls on a vegetational cover, not all the sun energy will be trapped by these green plants or vegetational cover. What happens is, from studies, it has been shown or discovered that about 20% will be reflected back to space. So if it was 100% sun rays on the vegetational cover, not all of them will be absorbed by the plants. 20% will be sent back to space. How many will be left? 80%. 39% will be used in evaporating water from leaves by transpiration. Of course, the process of transpiration requires energy. And so 39% of this 80% left will be used to carry out transpiration by these vegetational covers. And then 40% warms up the soil, air, and plants. 40% of the sun rays will be used to warm up the soil, the air, and the plants. So the most important thing we're looking at is that it's only 1% that will be left to be used in photosynthesis by the green plants. So each of the green plants, each of them in that vegetation will be left with only 1% to be used to carry out their photosynthesis. So take note that it is not 100% that will be used for photosynthesis. Only 1% that the plants will have left to carry out photosynthesis. Only 1% of the solar energy which has fallen on the plants will be used for photosynthesis. A whopping 20% will be reflected back to space. 39% will be used for transpiration. 40% for warming up. Only 1% will be left for that plant to use for its photosynthesis. This is what we mean by energy loss, because this is not efficient at all. Only 1% of the 100% that fell on the plant will be used for photosynthesis. Imagine a whole 99% not used for photosynthesis. That means food supply is already short. That means there will not be enough food for the primary consumer and along the food chain. Imagine if all of them, or say 50%, was used for photosynthesis. That's more food for the plants and even the consumers. But this one, only 1%. So what happens to the rest? It means that 40% was lost as heat because it was used for warming up. Even 39%, it takes heat for transpiration to occur, as it is heat that will actually evaporate off the water from the leaves. 20% is reflected back, so about 79% was lost as heat. Even though part of this heat can play useful function. For example, the 39% of transpiration can be used again in the hydrologic cycle to replenish the water cycle so we don't run out of water. However, we are not looking at those. We are looking at the fact that a whopping 79% was lost as heat. 20% was only given back to space. But 79% heat whether for transpiration purpose or for warming up the soil, air, and plants. But only 1% was left for photosynthesis. So this is what we mean by energy loss in the form of heat in the ecosystem. So the form of energy loss in nature is heat energy. Heat energy is the form that energy can be lost in any ecosystem or in nature. So energy, I repeat, is lost as only heat or in the form of heat in an ecosystem or in nature. And this is what the second law of thermodynamics is talking about. Let's take another example. So the first one we looked at was plants. What about animals? Remember we said that plants and animals will be the media of conversions, and hence the release of heat to the surroundings during these conversions by these plants and animals. Let's take an example of an animal being a conventional medium and heat being released in the process to the surroundings. Now, when energy in the grass is transferred to a cow, that means when a cow feeds on grass, of course it taps chemical energy, right? So when energy in the grass is transferred to a cow, 60% passes through the cow undigested, 30% is used by the cow in respiration to provide energy for life processes, and only 10% is converted to new tissue for growth. So what is this talking about? That a whopping 60% is lost. This is energy loss in nature. Why nature? Because it involves plants and animals. So a whopping 60% passes through the cow undigested. That means it's lost. Maybe through urination, defecation, or even as sweat. It's just lost. Maybe it will be defecated. Just lost somehow. What happens to the remaining 40% if 60% is already lost? Now, it means that what we're saying is that as the cow feeds on the grass, it has lost 60% just like that. Excuse me. No specific use. What about the 40%? Now, 30% is used by the cow in respiration to provide energy for life processes, okay? So 30% is used for metabolic activities of the cow. Good enough. At least it's useful. What about 10%? Only 10% is converted to new tissue for growth. Only 10% is passed on or is stored by the green plants as biomass. So it means that the primary consumer we have just about, it will fetch from this 10% its food. So of the 100% energy or chemical energy that the cow got from the grass, only 10% can be tapped from by the next feeder. And the next feeder will be a what? Secondary consumer. The grass is the primary producer. The cow is a primary consumer. So whatever we feed on the cow is the secondary consumer. And now this secondary consumer, which could be man, will have only 10% to tap from. A whooping 90% is not represented. Only 10%. Whatever benefits that this secondary consumer will tap from in terms of chemical energy will come from only this 10%, which is the biomass stored up in the cow. So this is what we are talking about, energy loss, because the cow will feed so much, the plant will take so much, or will take so much solar energy. By the end of the day, whatever it's left stored up to be passed on to the next consumer is so minute or too little as compared to what was given to that initial trophic level representative. I hope you're understanding. Let's talk about the gross primary productivity of the ecosystem and the NPP, or the net primary productivity of the ecosystem. Now, when we talk about the gross primary productivity of the ecosystem, GPP for short, this is the rate at which primary producers manufacture food per unit area, per unit time. And take note that it varies with the type of producer. So the rate at which primary producers, the rate, that is how fast per time, productivity per time, okay? Now the rate at which primary producers manufacture food per unit area, per unit time. That's the gross primary productivity. So it's very specific with the primary producers, which could be your green plants, okay? Which are your green plants actually? Because here we are talking about photosynthetic ones. We're not actually looking at the chemosynthetic organisms. So here we are being specific about the green plants, photosynthetic organisms, green plants, okay? So the rate at which primary producers or your green plants will manufacture food within a given area, within a unit time, within a unit area, within a unit time, is what we talk about as gross. That's gross. When you say gross, that's like the largest. Gross, that's the largest productivity of the green plants per time. And of course it varies with the type of producer. Now about 30% of this food is used by the producers. The remainder that is stored is called the net primary productivity. So about 30% of the GPP, take note, about 30% of the GPP of all the productivity, possible production made by the green plant, about 30% will be used by the green plant for its metabolic activities, such as respiration, growth, and development. After it has used 30% for its metabolic activities, and aside the portion that will be lost as heat, now whatever will be stored or left to be transferred to the next trophic level is called the net primary productivity. That is the NPP. Net is like the profit, the gain remaining. And then NPP determines the food which is available directly or indirectly to all the consumers in an ecosystem. Let's take a look at this. turn with me to get your textbook, Modern Biology. Okay, let's look there. Turn to page 123 of your Modern Biology textbook. Okay, under functioning ecosystem. Okay, go to figure 6 to 7. You see a cow there. Are you there? Okay, I want to talk about this picture. What is this picture all about? Are you there? I'll give you time. Remember, we're talking about energy loss in nature, and the form of this energy loss is heat energy. The form of energy loss in nature is heat energy. The form of energy loss in an ecosystem is heat energy. Heat will be dispersed. That's second law of thermodynamics. Okay, I trust you're there. All right, so now in this figure 6 to 7, you see a cow there. You see the solar energy, which is the ultimate source of energy in any ecosystem. And then you see the cow. There are cattle egrets. Okay. All right, so the NPP of the grassland in that picture is shown to be 21,000 kilojoules per meter square per year. That should be meter square. Okay, so that 2 should be raised to power 2. M raised to power 2. Okay, should be superscript. All right, so take note that the NPP, or the net primary productivity of the grassland that the cow is feeding from, is shown to be 21,000 kilojoules per meter square per year. So energy per unit area per unit time. The unit area is meter square. The unit time is year, yearly basis per year. Okay, so the cow consumes 3,000 kilojoules. All right. The cow consumes 3,000 kilojoules. So if I was to ask you, what percentage does the cow consume? Now, if the cow consumes 3,000 kilojoules, it will be 3,000 kilojoules per 21,000 kilojoules times 100/1. So you'll be left with what? About that will give us about 14%. Okay, so the cow consumes 3,000 kilojoules. So from the possible consumption, okay, because the grassland is having net primary productivity of 21,000 kilojoules. In other words, aside all it has lost as heat to the surroundings, aside all it has used for its metabolic activities, it has stored up in it to be transferred to the next trophic level, 21,000 kilojoules. Now, kilojoules here is just the unit of energy. Joules is the SI unit of energy, right? Now kilojoules times 10 raised to power 3. That's a higher unit of energy. Okay, now the cow consumes just 3,000 kilojoules, even though it's having a vast of about 21,000 to consume from, but it was able to consume, as at that time and that rate, okay, it could just consume about 3,000 kilojoules. All right, now nearly 2/3 of this energy is lost through its urine and feces. Are you following? Nearly 2/3 of this energy that it has consumed is lost through its urine and feces. That means 2/3 of 3,000 kilojoules will give us what? 2,000, right? Okay, to give us 2,000 kilojoules lost, undigested, lost through its urine and feces. So when the cow defecates, when it urinates, it also releases energy alongside. So a whooping 2,000 lost in urination and feces. That's what we mean when we're talking about energy lost in nature. Of course, if you touch the urine, it's kind of warm. Even the feces is warm too. So heat energy lost. Now take note that the form of the energy as it has consumed is chemical energy. All right, the food it eats is in the form of chemical energy, but when it is lost, it's lost as heat energy. So the energy is lost through urine and feces. So how many will be remaining? 1,000 kilojoules. That's 1/3. So the remaining 1/3, that is 1,000 kilojoules, will be absorbed. That is, how did we get 1,000 kilojoules? 1/3 of the 3,000 kilojoules. That is 1,000 kilojoules will be absorbed in its body as the biomass, to be used for new tissues, new cell formation. So it has only 1,000 kilojoules. It was able to absorb and use as biomass 1,000 kilojoules, having lost 2,000. Only 1,000 from these 3,000 can be passed on or is stored up in its body and can be fed from by the next trophic level representative. Now let's continue. Nearly 80%, that is 800 kilojoules, is lost as heat through its activities. Wow. Now this 1,000 kilojoules is absorbed. That means it's still having in reserve or stored up in its flesh about 1,000 kilojoules. However, it began to jump around, roam around. It was not contained perhaps in a pen. So it started moving around, thereby maybe running around, thereby losing energy still. So from this 1,000 kilojoules that is supposed to be left for the next user, 80% was lost from this 1,000 kilojoules. So 80% of 1,000 kilojoules is what? 800 kilojoules. That's 80 over 100 times what? 1,000 over 1. So that will give us what? 800 kilojoules. This is lost as heat through its activities. Now if 800 was lost, what will be remaining? 200 kilojoules. How small? Now the 200 kilojoules is converted into new tissue in its body. So the 200 kilojoules is the new one left. That's just the quantity left, having lost 800 kilojoules of its stored energy that was supposed to be a reservoir or a reserve for the next user, but it went on, carried out some of its regular activities, and it lost 800 kilojoules as heat to the surroundings, so it's leaving only 200 kilojoules for the next user. What does this mean? This means that only 7% of the food energy it consumes is stored in its body. This means that only 7% of the food energy it consumes is stored in its body. How did we get the 7%? The 200 kilojoules of biomass, okay, divided by the 3000 kilojoules that it fed from, times 100/1. Are you following? That's how we got the 7%. Are you following? So if you do 200 kilojoules divided by 3000 kilojoules that it was able to feed from, times 100/1. If you cancel out, kilojoules cancel out kilojoules, and then you have 7%. So that's how we got 7%. That's the interpretation, that only 7% of the food energy it consumes is stored in its body. That's only 7% will be the new biomass left for the consumer, next consumer, which is probably a secondary consumer. Yeah. So you can imagine that it was able to feed from 21,000. It was able to feed out. It was able to get 3,000 kilojoules. It fed 3,000 kilojoules. So it had 3,000 kilojoules, whooping 3,000 kilojoules, but only 200 kilojoules will be given to the next consumer. Although not all, but that's the reserve from whence the next consumer could feed from. Of course, the next consumer won't be able to feed everything, feed on every 200 kilojoules. No, it will just get a portion that it can feed from. But you see how this biomass is reducing as it goes along the food chain. That's why I will say that the biomass is decreasing, the energy is decreasing as you move away from the producer, going further into the consumers. So only 200 kilojoules will be left for the next consumer, the secondary consumer, to feed from. Even though the initial consumer fed and had about 3,000 kilojoules of chemical energy. But what happened to, if you subtract 200 from 3,000, that'll be 28. So what happened to about 2,800 kilojoules? Now, if the portion it actually used for its metabolic activities may not even be a problem, but the portion that was lost, just lost like that, it's really a loss, and this loss happens in the form of heat energy. Okay, now this 7% is only 1% of the NPP of the grassland. True? How will you know? This 7% is only 1% of the NPP of the grassland. How do we get the 1%? Now, the 200 kilojoules of energy, okay, that is the biomass left for the next consumer, divided by the total NPP of the grassland, which was 21,000 kilojoules, times 100 over 1. That is 1%, approximately 1%. Okay. So only 1% of the whopping 21,000 kilojoules per meter square per year, only 1%, okay, will be left for the secondary consumer. Only 1%. Of 21,000 kilojoules of energy of the grassland, as much as 21,000 kilojoules, only 1% is what the secondary consumer or the next consumer that will feed on the cow will have to feed from. That's too small. So this is where the loss comes in. So this is what we mean by energy loss in nature, because the primary consumer can feed a lot, but the biomass left for the next trophic level consumer is rather too small, unjustifiably too small, and this is a great loss. When we talk about the plants, they were able to harness, they got so much ultraviolet light rays, but at the end of the day, only 1% for photosynthesis. Wow, that's just a big loss. You see what we mean? I don't know if time will permit us, but let's quickly look into some of the questions. Now, the question says, justify the statement that NPP is higher in tropical ecosystems where plants grow all year than in temperate ecosystems. Why is it that the net primary productivity, that is the biomass left for the next trophic level, why is it that it is higher in tropical ecosystems than in temperate ecosystems? Did you get the question? Why is it that the chemical energy on reserve for the next trophic level feeder is higher where in the tropical ecosystems? That means that the next trophic level consumer will have more chemical energy to feed from than in temperate regions. Well, the only justifiable reason would be that because in the tropical ecosystems, plants are actually growing. We have more trees, more plants. So because of these, it only means that since there is flourishing growth, it means there is more chemical energy. It means that the productivity there is high. So there is a tendency that more chemical energy will be stored for the next user. It means that the plants, the green plants, were able to photosynthesize more. They made more food, and hence they had more reserve. So there will be more chemical energy for the next one because there are more plants. It means the productivity in that ecosystem is high. Hence, the more plants. And because productivity is high in such ecosystem, then there will be more chemical energy on reserve for the next trophic level user. What do you think? All right, so another thing, when the sun ray falls on the vegetational cover, if they are actually much, there is the tendency, like if the plants there are more, there is the tendency that the soil is also rich in nutrients for there to be many plants, because there are more plants in tropical regions. So for the fact that there are more plants, it means productivity there is more. It means there are good soils, sufficient solar energy for more photosynthetic activities, and because of this, it's just like you're having enough or sufficient food for yourself, and you are rich enough to keep on reserve for the days of famine, so to say. So if you have availability of food for yourself, if you have availability of food, there's the tendency that you will have food reserves for the days of famine. So it's just the same way here. The tropical ecosystem has lots of plants, more than the temperate regions. So it means that the productivity there is high, the photosynthetic activities there is high. And because it's high, more chemical energy, more food. And so, more food will be stored for the next trophic level user. I believe that's clear. Then number 2, long or short food chains, which is more beneficial to man? What do you think? Short, right? Yeah. Imagine maize plants, straight away man, like you have in your example in your textbook. If you look at page 125, okay, you have food chain. 2 food chains were shown: maize plants, and then man as the primary consumer. And then the second one, you have maize, then hen, then man as the secondary consumer. Which one do you think is more beneficial to man? Is the short one. Why? Remember that as you go along the food chain, as you go farther away from the primary consumer, from the primary producer, the green plants, okay, the energy decreases. So whatever man we get in the short food chain, okay, would have been depleted, would have been cut for man in the longer food chain. So man will have lesser energy, lesser chemical energy, lesser biomass to feed from, lesser NPP when it's longer, unlike when it's short. So man will have more chemical energy, more food to tap from in a shorter food chain than in a longer one. So the one that is more beneficial to man is the short food chain. Is that clear? Man feeding straight away on the maize, man gets energy But if it will feed on the hen that feeds on the maize, it will get 1/10 of what it would have gotten if it fed directly on the maize. So if man was feeding on the maize, if you should get, for example, 50 kilojoules, if it was to feed on the hen, it will get 1/10 of that 50, and that's just 5 kilojoules of energy. So the more the energy derived, it means that man got more food. Okay, so number 4, what can man do to primary consumers such as hens and goats so as to derive a higher NPP from them? Okay, if man wants to derive higher chemical energy from hens and goats, then he should put them in pens or in cages so that they don't roam around wasting energy or losing energy in the form of heat. If they run around, they waste energy in the form of heat. But if they will be contained, put in a cage, then that excess exercise wherein they lose energy will be contained, and that means energy will be conserved for man to tap from as chemical energy or food. So that's what man can possibly do. Let him put them in cages so they don't run around wasting energy and losing energy that would have been chemical energy for man as heat energy when they run around. I'll show you something quickly. These calculations, we'll look at them later on. I just want to show you we'll look at the calculations later. I just want to show you a summary of the fate of solar energy absorbed by leaf. You also have it in your textbook. I think if you go to page 123 of your textbook, it's just the summary of the fate of solar energy. So you see that leaf absorbs 100 units of solar energy, okay? 75 units will be lost as heat. Only 25 units will be changed to chemical energy in food. So this is what heat loss is, energy loss is all about. Imagine 75% of 100 lost as heat, only 25% or 25 units rather, available as food. What happened to the rest 75 lost as heat? That's what we're talking about. Energy loss in the form of heat, second law of thermodynamics. And then in this 25 units, how many only 7.5 units used by plants for its activities. Okay, so 7.5 units will be used by plants for its metabolic activities. That is 30%, right? 30% of 25 units. That's 7.5. So 30% of these 25 units, which is available as food, will be used by plants for its metabolic activities. Then the 17.5, that's the leaf we're talking about, will be used by the leaf for its metabolic activity, okay, such as maybe respiration, okay, growth and development. Now 17.5 units left, that is 25 minus 7.5 units, you have 17.5 units left. This is the part that will be stored in plants and available for the primary consumer. Let's explain it again. Now, a leaf absorbed 100 units of solar energy. Now, in this 100 units, 75 units was lost as heat to the surroundings, according to second law of thermodynamics. Now 25 units was converted to food. In other words, 1/4 or 25%, right, of the 100 units, 1/4 of 100 units or 25% of 100 units was changed to chemical energy in food. That is, was used for photosynthetic activities. But a larger portion of 75 units was lost as heat. Now, in these 25 units, all of them were not available as biomass to the next trophic level representative or consumer. Within these 25 units, a whopping 7.5 units was used by the leaf for its metabolic activities: digestion, respiration, growth and development. Okay, then only 17.5 units is available as NPP, or is the biomass available for the next trophic level consumer. So this 17.5 units stored in plants available for the primary consumer, that is NPP. You see, so from a whopping 100 units of solar energy, only 25 units was used for photosynthesis, and only 17.5 units is available as NPP. So this is what we're talking about, that energy is lost in nature in the form of heat. This justifies the second law of thermodynamics. And for the fact that solar energy can be converted to chemical energy, and chemical energy converted to lost as heat energy, this also justifies the first law of thermodynamics. We'll stop here today. Thank you for being there. God bless you.